All right, so just recapping a little bit of what we did yesterday, we said that we're now going to start measuring some stuff with another system called radians. So we can measure theta in degrees or radians. We said that a circle has 360 degrees or 2 pi radian. And 2 pi radian, or just radian in general, we use because it comes to work really nicely with our trig functions, and a lot of our results are really nice when we go to use it. It's also just a little intuitive to talk about the circle in terms of pi and stuff like that, since circle is pi and all that. Cool. We talked about arc length. So if I have a circle and I'm talking about an angle, say theta, then the amount of the circumference spanned by that we call S, which is the arc length. They used S because A and L and all that had already been taken, but you can think of it as how much is spanned by that angle. So what portion of the entire circumference is spanned by that angle there? We can think about it in terms of the portion of the angle to the entire thing. So if we're talking in radians, then theta over 2 pi, so theta over the entire span of the angle, is equivalent to our arc length over the entirety of 2 pi r. And then canceling out those 2 pi's on both sides, we see that theta equals S over r, or arc length is theta times r, where theta is in radians. That's another reason why we use radians. It makes it a lot easier to talk about arc length. This will be important to remember for when we revisit our example we did with angular velocity yesterday, so I'm just going to write it up here. Arc length is proportional to the radius times the angle subtended. Cool. One thing I didn't mention, but is logically similar to this, is completely forgot the word for it. It's the area spanned by this. What is the actual word for it? So I can tell y'all. Oh, area of a sector. So we can talk about the length spanned of the circumference, or we can talk about the area which with this spans out. So that area, that red area, which I'll just call A sub sec, or sect, this is area of sector. Right, think of it like a section of the entire area. It's an area of the sector. So you just take the entire area. Remember, the entire area is pi r squared. Right, and we're finding out what portion it is. So if my A sect over pi r squared is proportional to whatever my angle is over the entire 2 pi. I can cancel out those pi's. A sect equals theta r squared over 2. So the area of this portion is equal to this area. This like over 2, you can kind of think about it as like a 1/2 base times height, basically. Right? Triangle, this looks like a triangle getting spanned out. That's exactly what we're talking about here. We're talking about this little piece right here. Cool. This necessarily isn't super relevant to remember, but it might be convenient to have that written down. So just having an area there, and we can go back and forth when talking about certain things. All right. Revisiting this idea of arc length right here, we were talking instead about angular velocity, so how the angle changes over time. Remember, regular velocity is equal to change in position. I'm going to use a capital delta here for change in position over change in time. Right? For instance, I'm talking about 20 miles per hour. I'm changing 20 miles in the span of 1 hour. So the change in position is 20 miles, the change in time is 1 hour. if we want to instead talk about angular velocity, this top one is actually called linear. We're going in a straight line, linear velocity. Angular velocity equals change in angle over change in time. At the end of our example, our angular velocity came out to be in units of radians per second. Linear velocity was feet per second. Radians per second or degrees per second or something like that is typically how we talk about the units of angular velocity there. And so the example we were looking at specifically was if I have some sort of, maybe a pulley or something like that, and I've got some sort of mass that I'm trying to lift with it.
Is that O time? Is that?
Oh, delta.
Oh,
Capital delta is a triangle.
thanks, yeah. I was confused.
You're good. So if I know how fast around this is spinning, maybe I know the RPMs of the motor that's spinning it or something, and I can figure out how fast up this is traveling. So this position over time, I'm thinking about the change in position as how much the cord would be wrapping around this, for instance. So this is going to be my arc length that I change. That's going to be my distance, or my change in position, over time. Then the change in angle is just the angle span, which I'm going to say is theta, over time. But I wrote arc length in terms of theta over here. So I can relate my linear velocity with my angular velocity. Remember, for linear velocity we use v, angular velocity we use omega. Sometimes in physics courses you'll also use the Greek letter that's nu, nu, as velocity, but we'll just use v for now. So I can rewrite this linear velocity in terms of this angular velocity, right? So v is s over t, but s is theta r over t, and then I have my theta over t right there. So I get omega r. So it makes sense, omega, the amount that I'm spanning here, is proportional to the velocity. The velocity is proportional to how fast this is turning around and then how big the circle is, right? If I have a bigger circle that's spinning faster, this should be going up more, right? Think about it like if I were to spin like a plate or something at 1 rotation per minute, that'd be really slow. But the entire Earth, if it spun at 1 rotation per minute, would be insanely fast. That actually might fling everybody off because of how fast that would be. We do 1 rotation every 1,440 minutes instead. So if the Earth spun 1,400 times faster, we would probably feel it. You think it's a bigger circle, even though they're spinning the same speed, the outside speed is different because the circle's so much bigger. All right. So our example was specifically that our radius of our pulley was 2. We can use whatever unit we like. I'll just use inches because it's easy to write. And I know that my rotational speed, which I'll write as omega for now, but it's not in terms of angles, it's in terms of revolutions, is 8 revolutions every 15 seconds. Or 8/15 revolutions per second. Just to keep the units over by themselves, but it's 8 revolutions per 15 seconds was the setup we had. We then wanted to rewrite omega in terms of radians per second. 1 revolution is how many radians? How many degrees is a full spin around? 360. And then how many times does the radius wrap around a full circle? 2 pi. So 1 revolution or rotation, you can think of it either way, is 2 pi radian. Remember, our circle as a whole is 2 pi radian, so 1 rotation, the angle changes by 2 pi radian. So my omega is 8/15, 2 pi radian per second. And then 8 times 2 that's supposed to be 15, not 18, apologies. And then 2 times 8 is 16 pi over 15 radians per second. So that's how much the speed of the angle is changing. How fast the angle is changing? Well, it changes 16 pi over 15 radian every second, which is a little more than like here. It's a little past halfway every second, which makes sense. If 8 over 15 is a little over half, then the angle should change a little over half the circle every second. So then I have my omega. My v is just omega times r, so that's going to be 16 pi over 15. My radius was 2. And then now we're talking about linear velocity, so what's going to be the units of that? Inches per second, right? It doesn't make sense to talk about I'm walking this fast in angles. I'm walking this fast in inches per second or something like that. So times 2, and then this is inches per second, which would be 32 pi over 15. And then that's inches per second. So we're just talking about, if I know how much this is turning, this is going up. Cool. This example specifically is very, very useful for anyone who has to take a physics class or mechanics class, statics, anything like that. You're going to talk a lot about angular velocity and stuff like that. Any questions about this? And again, this is recorded, so you can go through and rewatch this as many times as you need finally, and have that. One thing that I didn't mention that would be useful to mention, I'll get rid of this stuff over here. Is coterminal angles. So we first talked about the standard position of an angle. That's just what it looks like if I map it from the x-axis. So it doesn't matter what it is. Say this is my angle right here. I could have wrapped around 20 times, but this is where it ends up. So the final position. Final position, and specifically on the xy plane. Right, we can think about the final position like as a point on the xy plane or something like that. Maybe I've wrapped around a couple of times on here. Two angles are coterminal if they have the same standard position. So what would happen to this point if I were to wrap around 360 degrees again? It'd be in the same spot. That means it's coterminal. So if I were to instead say that my angle has done this, maybe this is angle phi, then theta and phi are what we call coterminal. They end up in the same position relative to the x-axis specifically. What's the word? Coterminal. I'll write that out. Terminal means ending. Co means same. So same ending. Or with, together, ending, something like that. So for instance, if we're talking in degrees, and I'll write this out like a little table, versus radians, any multiple of 360 degrees will get me back in the same place. So theta plus 360 times some number of degrees, where n is a integer, maybe. You remember the symbol for integers from pre-calculus algebra? If you don't, this is the symbol for integers. That's just whole positive and negative numbers. It's supposed to be a z, but I drew it sideways. Right? Integers, we use z because the word for number in German is Zumba, which starts with a z. Versus radians, we said a circle has 2 pi radians. So if I go around 2 pi radians, I get back to the same point. So it's any angle plus 2 pi times any integer radians. Or again, n is some whole number, positive or negative. So for instance, if I got to this point and then I wrapped around 720 degrees, I get back to the same point. I've just gone around twice. Or negative 360 degrees will wrap me back around but going the other way, for instance. Cool. So those are coterminal angles. There might be a couple questions in the homework about finding coterminal angles. I know there were quite a few in the book when I looked through it, so there might be some there. Any questions about coterminal angles? Or standard position or anything? Y'all are free to ask any questions that y'all want. I haven't asked. Yes.
Wait, can you explain the degrees, like the bottom one? Like I know that's the any angle plus 360, but like the bottom ones? The one that, yeah, what would you call it again?
Any number in the integers. So, I'll write it out. Number in integers. Did y'all not see this in your pre-calculus algebra class?
I remember that number.
Who did see this in pre-calculus algebra? Who did not see this in pre-calculus algebra?
Oh.
You did not see this in pre-calculus algebra? Your teacher needs to be fired. That is day one pre-calculus algebra. So, if you feel a little rusty on your pre-calculus algebra, the link on the website to the notes for y'all, it's the same book. It's just one big pre-calculus algebra book or pre-calculus book that I'm doing. So, if you want to review some of your pre-calculus algebra, the first couple sections of my notes are also in there. I didn't give y'all the link to my website. I can write it, I guess, up here. https sites.google.com/view/Jackson-Lewis-math. And then you can click on the teaching tab, and under that is the notes if you want to access it. Yeah, you can take a picture of that if you want to. Those words, you can't read them, but it's my name, Jackson-Lewis-math. My name's not math, but Jackson says it. Cool. All right. Very good. One thing that I've also included in the notes, or I will include in the notes, is remember a squared plus b squared equals c squared? I wrote out a list of numbers that follow that are pretty useful to have. For example, 3, 4, 5, and 5, 12, 13 are some of the most common. Those are possible sides or scaling them of right triangles that follow that. So y'all have that too. All right. Now we'll actually talk about some right triangle trig. Who remembers or has seen like SOHCAHTOA before when talking about angles? Who has taken any trig before? That might be a better question. Or maybe I should say who hasn't taken any trig before. A couple of y'all. Okay.
Does junior math count as trig? Because we had trigonometry as like a unit, but it wasn't like that.
If it wasn't the whole, I went to school in Georgia, so I have no idea how y'all do it here. I also did like different classes in high school because I took all the high school math classes when I was in, I guess, 8th grade. So I don't know what the standards are for North Carolina public education. I'd assume they're probably the same though. So if you saw it for a unit or two in like Math 1 or Math 2 or whatever in high school, then yeah, you've seen some of this. I don't imagine many people take an actual entire class on trigonometry in high school though. Cool. All right, so we're talking about right triangle trig. I'll draw it like this. Let that be my angle theta. So we've been talking about, like when I label a triangle, I usually say like A, B, C, and they follow the A squared plus B squared equals C squared. I'm going to label them a different way. First, I'm going to consider this angle right here to be the angle I'm looking at. I can redraw my triangle however I want to, but this is for now going to be my angle. However you want to draw it, if you want to talk about this angle, you can, but we're talking about this angle. Across from it, on the direct opposite side, I'm going to call this the opposite side. Or just op. The side directly beside it, I'm going to call the adjacent side. or just ADJ. And then does anyone remember what the longest side of a triangle is called? Hypotenuse. I actually don't know how to spell it because it has a weird E and a U somewhere.
Hypotenuse.
Yeah, it's like there's this weird EU type of thing in here, and I don't know if that's actually how it is, but it's somewhere in there, hypotenuse. But I'm just gonna write it. The three main functions that we talk about in trig are sine of theta, cosine of theta, and tangent of theta. And spelt out, that's sine, cosine, and tangent. So they take in an angle as their argument, right? The thing that the function takes in is the argument. And then it spits out a number. Cool. We have a good mnemonic device to remember what these relations are in terms of opposite and adjacent. And we say so ka toa. You can remember that however you want. You can like actually sound it out and write it. There are a couple of you can make up sentences to remember if you want to. But a lot of people just remember the words so ka toa and spell everything out. So goes with sine. It means the sine is opposite over hypotenuse. So whatever the length of this side is, divided by the length of the hypotenuse. That will give you the value of sine theta. Ka goes with cosine, and that means adjacent over hypotenuse. And then toa goes with tangent, and that means opposite over adjacent. It also is, in terms of these other two, equal to sine over cosine. So again, these are functions that if I know the angle, I can tell you just about anything else about the circle. Or if I know the lengths of the circle, I can tell you about the angles that the lengths of the sides, I can tell you about the angles inside the triangle. So soka, toa, sine, cosine, tangent, those are our three important functions. There are three more functions which are the reciprocal functions of these. These are a little more difficult to remember, so just write them down and kind of go over them a couple of times in your head. These are secant, cosecant, and cotangent. And these just mean take one over the other function. So this is 1 over sine, this is 1 over cosine, and 1 over tangent. Those are somewhat useful in certain instances, but it's also just required that y'all are familiar with them for this class.
So it's basically the reciprocal of the original function?
They are the reciprocals. These are reciprocal functions. Reciprocal functions. It's important not to get them confused with inverse functions. So cosecant 1 over sine is not the same as inverse sine, which we'll talk about in a couple of days, I think. Cool. The important three to remember are these, and then they have the reciprocals that go with them that are useful in some instances. Cool. So we could do a little example with this. Say we have some triangle with an angle, theta, and I know about it that the cosine of this angle is 3/4. Cool. So that means that cosine, ka, the adjacent is 3, and the hypotenuse is 4. How could I find this missing side right here? Pythagorean theorem, right? I remember that a squared plus b squared equals c squared. I have a, which is 3 squared. I don't have b, so I'll solve for that. And c squared is 4 squared. So this is 9 plus b squared equals 16. B squared equals 7, so b equals the square root of 7. Cool. If you've seen triangles before, your first instinct might be 3, 4, and then 5, because 3, 4, 5 is a Pythagorean triple, but it's important to note that the hypotenuse is 4, not the opposite side. And then square root of 7, I want to say, is probably like 2.3-ish. Something like that. You don't have to know what that value is. But like on all your tests or anything, I'll have you just leave it as square root of 7. I don't want the decimals. I want the exact answer, which is square root of 7. Cool. So now that I have that, I can find sine. Right? Sine was what? Opposite over hypotenuse. My opposite is the square root of 7. My hypotenuse is 4. Tangent was opposite over adjacent. So the tangent of my angle, opposite, is the square root of 7 over the adjacent, which is 3. Cool. And then I can find all of my reciprocal functions as well. Secant would be 4/3. Cosecant would be 4 over root 7. Cotangent would be 3 over root 7, for example. Any questions about these? Right. Good deal. Now we can do a couple of examples with these, some more realistic examples. Say I'll get a little comfortable with how to solve trig problems. Cool. Any questions about this before I move on? Cool. All right. Has everyone gotten this written down or taken a picture of? I'm good to erase it. All right. So our first example is I have some tree. Beautiful tree. And the shadow that it casts is 532 feet. And the sun, just beautiful, is at an angle of elevation of 27 or 25.7 degrees. I'm just pulling this from the book. I'll use this marker. That's terrible. So this is theta. Theta equals 25.7 degrees. We'll do these examples starting in degrees first so that y'all are a little more comfortable with the measurements and everything. We'll eventually move to doing everything in radians though. Cool. So the question is, how tall is the tree? I'll just let that be T for the height of the tree. Well, what information do we have? We have theta, and we have the adjacent side, and I want the opposite side. Which function has both the adjacent and the opposite side in it? Tangent. Cosine has hypotenuse in it. Co, though, has opposite, but then you have hypotenuse there. So we have tangent of theta equals opposite over adjacent. Cool. So that means that tan of my angle 25.7 degrees, I'm going to put degrees because it's important to remember what you're working with when you put it in your calculator, is equal to the opposite, which I don't know, T, over adjacent, which is 532. And then how would I solve for t here? Multiply both sides by 532. So the height of my tree is 532 tan 25.7, which works out to about 256 feet. Did anyone get a different answer?
I can't tell if I used degrees or radians.
You can change that on that calculator. I think you have to go to the either mode or setup and change it. Let's see. Mine is in degrees, so I think I'm screwed. If anyone wants to verify this answer, you're more than welcome to. If I had it wrong. Good?
Oh, there we go.
There we go. Cool. So the height of the tree is 256 feet, and all I had to know from that is how high the sun was and the length of the shadow it cast. That's a bit of weird information to have if you're out hiking in the woods, but maybe you know that the angle of elevation of the sun is actually 90 degrees because it's noon, and you can measure the shadow, then you can tell how tall the tree is. That's something cool that you can do. I say cool. I think it'd be cool. All right. Any questions about this problem? Any questions at all? This is about as simple as the problems get. So if you have any questions about this or need any part of it redone, please ask now. All right. Now a little bit trickier of a problem, but it's not too difficult. Does everyone have this? Can I erase it? You're more than welcome to move this back. Just need some space. All right. The next one is I have a guy, maybe Bob, and he's standing 500 feet from a building. From Bob's line of sight to the top of the building, we're assuming Bob is 0 feet tall. I'll use blue for this. His line of sight to the top of the building is 24 degrees. There's also a flagpole, the flag on top of the building. And from the top of the flagpole to Bob, that angle is 27 degrees. I'm going to call this angle phi. It's another Greek letter that's often used for angles. And this first angle I'll let be theta. And the question is, how tall is the building? How tall is the flag on top of the building? Cool. Again, we want opposite side of my triangle that I formed, right? If this is the bottom side, it looks like a triangle. I want the opposite side. I have the adjacent side. Just like this, I'm going to use tangent. I'll start first with the blue stuff. So know that the tangent of theta, right, is opposite, which is the height of the building. I'll call that B. Note that the height of the flagpole, we don't know yet. What we can find is the height of the flagpole plus the height of the building. So this is going to be F plus B. From the base all the way to the top of the flagpole includes the building and then the flagpole on top of it. So B, and then this is F. This whole part here is F. All right. So the tangent of my angle is opposite, which is B, over adjacent, which is 500. And then very simply, B is 500 tan theta, and theta was 24 degrees. and punch that into my calculator. 500 tangent of 24. I get 222.6 feet. Did anyone get the same answer? Good, good, good. Cool. All right. So I know what B is. I'll just put that in there for right now. 222.6. And then I can find the height of the flagpole plus the building. And then I can just subtract out the height of the building. I can't just find the flagpole because then I'd have to have difference of angles, and I can't just subtract the angles. You have to have weird identities that we don't know yet. So I know that F plus B, I can use tan theta. Oh, tan phi here, we're using phi, the other angle. Tan phi, this is another way to write phi, and this is often how I write it. It's the same thing though. Equals all of this now, so F plus B divided by the adjacent side, which is 500. So anyone confused by where any of this came from? If you are, please raise your hand and I can read it. Cool. So tangent, opposite, which from the base where Bob is to the top of the flagpole, includes the flagpole and the building, F plus B, tangent of that over the adjacent side, which is 500. Cool. Then I'm solving for F here. That's going to be 500 tangent of phi minus this building. And that'll give me none. It'll give me my flagpole height. Cool. I know what B is. It's 222.6. So 500 tangent of 27. 500 tan 27. I get 254.7. So 254 point, oh that's actually 8. 254.8 minus 222.6 minus 222.6. I get the flagpole is 32.16 feet tall. That's a very good flagpole. So I get this little chunk here is 32.16 feet. Again, how I did that, I first had to find the height of the building because it's very easy. I could just go for that 24 right there. That gives me all of that. Because I then needed to know the height of the building to figure out the height of the flagpole, because all I know is from the ground to the top of the flagpole, which includes the building. So once I know the building, I can take that part out for my final answer and get just the flagpole. Any questions about this at all? That's all I really planned to cover today, so I'm going to call it a wrap here. If y'all have any questions about anything, come to my office hours, you can email me, anything like that, and y'all have a great rest of y'all's day.